Okay, hello class. Back again for another lecture today. So this is lecture on section 7.5, which is the beginning of really working out how to do systems, how to solve first order systems of equations. Okay, so we basically want to start to solve systems of the form x prime is a of x, is a times x. So I think of x as a vector of unknown functions, a column vector. We're going to start with constant coefficients. So A is the matrix Aij, where Aij is an element of real numbers, and I and j are numbers between 1 and n. And so as we saw last time, this is equivalent to the first order system. X1 prime is equal to A11 X1 plus up to A1n Xn, and so on. And then you have Xn prime is a n1 x1 up to a n xn. So each one of these is a first order linear homogeneous equation, okay, in the unknowns x1 up to xn. All right, so when we had a single equation, what we did to solve the first, the constant coefficient, when we had, for example, a second order equation, we'd guess a solution. So right now, what we're going to do is the same sort of thing. And I'm not going to tell you the guesses that people tried that didn't work, because that wouldn't be productive. But somebody sat around and looked at this equation star for that matrix equation star. And I'm going to emphasize this is a matrix equation. Okay, the matrix ODE. And they figured out, look, what if I guessed that X was of the form, a vector, let's call it C times e to the RT, where C is a constant vector and R is a possibly complex number, and both are to be determined. Okay? All right, then what would C and R have to satisfy? Well, what would X prime be? Since C is a constant, in other words, it doesn't depend on T. So it's what I mean by that, it's independent of T, okay? So then X prime is C, the constant. Now you differentiate this guy and you'll get an R e to the RT, okay? And so by the equation star R C e to the RT is to be equal to the constant matrix A times C e to the RT. And the only thing that's a matrix is this C. It's a column vector. Okay, so it's a column vector. And so this is, so now we can divide by e to the RT, because e to anything is never zero. So I'm not dividing by zero. And then we get the matrix RC is equal to AC. So R and C are going to have to satisfy this. And if you think about that for a second, that says C is an eigenvector for A corresponding to the eigenvalue R. And that's an eigenvalue of that matrix A. So in other words, we can solve this problem, a vector of this form, a column vector of this form, will be a solution when R is an eigenvalue of the matrix A and C is the corresponding eigenvector. Okay, so that means, therefore, to solve the equation star, we need to solve, let's call this one double star, and get n linearly independent eigenvectors. Okay, because we know to get a solution to that, we're going to need n of a system of n first order equations. We're going to need n linearly independent eigenvectors by one of the theorems we discussed last lecture. All right, so let's look at an example how you actually carry this out. Okay, how do we carry out these calculations? So let's start with an easy one. Let's start with the matrix A being 1, 1, 4, 1. Okay, and I want to solve. So here's the question: solve x prime equals ax. Okay, and find the general solution. Okay, so I look for so step one, find the eigenvalues of A. Now I just wrote R before, but we could just as well call them lambda like we did earlier. So I'm going to look for all the lambdas such that the determinant of A minus lambda I equals 0. Okay, so that says the determinant of the matrix. So here's A, and I subtract lambda off the main diagonal. That's what this does to something. It subtracts lambda off the main diagonal. So this will be 1 minus lambda 1, 4, 1 minus lambda. And the determinant of that matrix is 1 minus lambda squared minus 4. So this is lambda squared minus 2 lambda plus 1 minus 4. So that says 0 is lambda squared minus 2 lambda minus 3, which factors to lambda minus 2. Let's see. Lambda minus 3. What am I doing? Lambda minus 2. Lambda minus 3, lambda minus 1, lambda plus 1. Okay? All right, so that says the eigenvalues are 3, excuse me, and minus 1. Okay? So that's the first thing we need to do. The second step on solving something like this is find the corresponding eigenvectors. Now the EVEX is my abbreviation for eigenvectors. Okay, so let's start with lambda equals minus 1. So we have to do A minus a minus 1, so that'll be plus I, times the corresponding eigenvector that goes with minus 1 has to equal 0. And let's say this one, it's going to have two components. Let's call them x and y. Okay. So A plus the identity will give me the matrix 2, 1, 4, 2, right? Times this eigenvector, these are the things we have to find, equals 0, 0. Because that means the zero that stands for the zero matrix there, because it has to, because this is a matrix, this is a matrix, this is a column vector, you multiply it together, you get a column vector. Okay. So when we figure out what these equations say in words, I'm multiplying the matrix that says 2x plus y equals 0. And the second equation says 4x plus 2y equals 0. And notice these are the same equations. So you only need one of them because the second one doesn't tell you anything new. Okay, so that equation says that y is equal to minus 2x. So if we pick x equals 1, then y is minus 2. So the eigenvector, or an eigenvector, I should say, because any constant multiple of this will also be an eigenvector. An eigenvector corresponding to minus 1 is the eigenvector 1 minus 2. Okay, so that's one of them. Now the second one, when lambda is equal to 3. Okay, now we have to do lambda minus 3 times the identity. Whoa. Times the eigenvector that goes with 3 has to be equal to the 0 vector. And this guy is going to have two components. So I don't know, let's call them u and v. So a minus 3 times the identity will be minus 2, 1, 4, minus 2. And then it'll be times the vector uv is equal to the 0 vector. Okay, so that says that minus 2u plus v equals 0. That's what the first equation says by doing the matrix multiplication. And the second equation by the matrix multiplication says 4u minus 2v equals 0. And it's not hard to see that that's the same equation. So you only need one of them. That's actually a little check. When you have a 2 by 2 matrix, the second equation better be the same as the first or a multiple of it. Otherwise, you did something wrong. So this says v is equal to 2u. So one eigenvector would be x3 would be equal to, if I pick u equals 1, then v is 2. Okay. So now we have our two eigenvalues and our two corresponding eigenvectors. And how did we form the solutions? The solutions we saw from the first calculation is a solution is the eigenvector times e to the eigenvalue times t. Okay. So one solution is the eigenvector corresponding to minus 1 times e to the minus t. And another linearly independent one, we'll check that, is is 1, 2 times e to the 3t. Okay. Now, how do I know they're linearly independent? Well, because the eigenvalues corresponding to distinct roots, and 3 and minus 1 are distinct roots, are linearly independent. Another way you can check that they're linearly independent is you put them in the matrix as column vectors. And then you take the determinant of that matrix. And this will be 2 minus a minus 2. So that's 4. It's not equal to 0. Therefore, they're linearly independent. Okay, that's another way. So that says that, and by what am I mean? This one and this one are linearly independent. Okay, check. That's a quick way to check if you want. So that means that you have two linearly independent solutions of our matrix equation. So the general solution of the matrix equation is C1 times e to the minus t times the vector 1 minus 2 plus C2 e to the 3t times the vector 1, 2. Okay. So that's our solution to that first order system of equations, or in this case, which was written as a matrix system in this case. Okay, let's do one other one. And that's all there really is in this section. So it's not really hard, but there's a lot of calculations that go on in the background. So here's example 2. Let's look at the matrix. A is 0, 1, 1, 1, 0, 1, 1, 1, 0. And find the general solution of x prime equals ax. Okay. Now, if you look back in our last lecture, we used this exact matrix. And so when I say find the eigenvalues of A, in the last lecture, we saw lambda is equal to -1 and 2, and this guy had multiplicity 2. And this was a simple eigenvalue, multiplicity 1. Okay, in other words, so we looked at set the determinant of A minus lambda I equal to 0 and worked it out. Okay, and then the next step is to find the corresponding eigenvectors, which we did also in the last lecture. In the last lecture, we found 2 eigenvectors from -1. Now, I forget exactly what we called it, but I believe we called it x1 and x1, x minus 1, and then x minus 1 hat. And so let's see, we had the eigenvectors, I believe they were 0, sorry, 1, 0, 1, and x minus 1 hat was 0, 1, 1. Okay. All right, so we found those last time, and then we found the eigenvector that went with the eigenvalue 2, and that was an eigenvector 1, 1, 1. Okay, and it's not hard to check that these are linearly independent. Okay, one way to check it is to put it in the Wronskian, but another way is to notice, because A adjoint equals A. What is A adjoint again? Remember, A adjoint means A complex conjugate transpose. And if you take the transpose of this matrix, you get back the same matrix. Okay. So A is self-adjoint. And so it has a complete set of a fundamental set of eigenvectors. And so these are linearly independent. It's not hard to check because they correspond to distinct eigenvalues, and these two are clearly linearly independent. Okay, otherwise you can put them in the Wronskian and take the determinant of the matrix. Okay. So then the general solution, so all the hard work really is in this first part, finding the eigenvectors and the eigenvalues and the corresponding eigenvectors. If you remember, that took a while in the last lecture. So now our general solution is just going to be x of t is c1 e to the, let's do e to the minus t, times the first eigenvector that goes with that, plus c2 times e to the minus t, times the second eigenvector that goes with this, eigenvalue -1, and then plus, that's C2, and then plus C3 times e to the 2t times the eigenvector that went with 2. Okay. 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 And so that's really all there is to section 7.5. And it just takes practice and basically you just learn it, you're practicing calculating eigenvalues and eigenvectors. And then once you get them, as long as they're all real and distinct, then you should get a fundamental set of eigenvectors, and then the general solution can be written out that way. In the next two lectures, and basically the rest of the course is looking at the other two cases. One is where you get eigenvalues that are complex conjugates of each other, and how do we handle that in this setup. And then the third is when you get repeated eigenvalues, and you don't necessarily have a full set of eigenvectors by this easy method that we have, like in this case. And that's a much harder case to handle, that last one. So that'll take a little more time.